In the late 1980s, there was only one thing everyone was talking about. It wasn't Madonna's latest single, leg warmers, shoulder pads, or even big hair. It was ozone. Or more precisely, a vast, hulking great hole that had opened up in our planet's life support system, the ozone layer. And the culprit? Supervillain gases known as chlorofluorocarbons, or CFCs, found in everything from fridges to deodorants, and they were destroying the precious ozone in the stratosphere. By the late 80s, the hole was reaching sizes of around 22 million square kilometers. By 2040, the hole would have gone global. By 2050, the ozone layer could have collapsed entirely. Harmful UV radiation would come flooding through, causing huge increases in skin cancer, cataracts, and compromised immune systems. Plants and crops would be failing. The word uninhabitable was being used by leading scientists. Before climate change, this was the greatest environmental apocalypse of our age, and yet we don't seem to talk about it anymore. Is it because we actually fixed it? I'm James Stewart and you're watching Astrum Earth. Join me in this video as we discover the truth about the hole in the ozone layer. We'll get to the bottom of what it is, why it's there, and how humanity managed to fix it. And I'll explain why we might not be out of the woods just yet. For those of you that might be late to this ozone party, and even for those of you that aren't, it's worth going back to the basics to start things off. What actually is the ozone layer? Well, Earth's atmosphere is like a jacket, or several jackets, for our planet. There are 5 main layers. The bit we're most familiar with is the troposphere. This is where we live. The troposphere starts on Earth's surface and extends up to around 20 kilometers. Now, this actually varies depending on where you're standing, and no, I don't mean like on a mountain. It's around 18 to 20 kilometers at the equator, but only 6 kilometers at the poles. The troposphere is a hard-working layer. It provides the air we breathe, contains 99% of the atmosphere's water, and is where you'll find pretty much all of our weather. As you climb, the air gets thinner and colder. Next up is the stratosphere, which extends from around 6 to 50 kilometers above the Earth's surface. The only clouds that usually venture this high are cumulonimbus thunderclouds, whose tops just scrape the lowest part of the stratosphere, which is why they've got their distinctive anvil-shaped caps. They're sort of squashed against the ceiling of the atmospheric boundary. Commercial passenger jets fly in the lower stratosphere, trying to stay above the weather for a smoother ride. In the troposphere, temperatures fall as you climb, but in the stratosphere, they actually increase with altitude. And there's a reason for this, and it's actually the reason you're watching this video. This is where the ozone layer is. Beyond that is the mesosphere, the thermosphere, and the exosphere, and past that, well, that's space. And we've actually got a whole other channel for space, so if that's your thing, why not check it out after this video? Anyway, back to ozone. Every layer of the atmosphere has a specific job to do, and the ozone layer is possibly the most important of them all. But to understand why that is, we need to understand a bit more about what this vital layer is actually made of. We're all familiar with oxygen, O2, it's what we're all breathing in right now. Well, ozone is O3. That's 3 oxygen atoms combined to form a pale blue gas. You know that sort of sharp, fresh smell you often get just after a thunderstorm? Well, that is ozone. Ozone can be both a hero and a villain, and whether it's good or bad depends on where it is. Bad ozone is tropospheric, or ground level. It's a harmful air pollutant and often the main ingredient in smog. But good ozone is stratospheric. It hangs out around 15 to 35 kilometers above the Earth's surface and basically acts like a sunscreen for the planet. This is the ozone layer we've all heard of, and it blocks an incredible 98% of all harmful UV radiation. Yeah, 98%, it works hard. The vast majority of sunlight is what's known as visible light, the light we can see, with wavelengths of 400 to 700 nanometers. Ultraviolet radiation is actually only 8% of all light, and it's invisible to the human eye, though some insects, like bumblebees, can see it. Visible light consists of different colours that you can see in a rainbow, and UV is no different. It also has its own spectrum: UVA, UVB and UVC. They're classified by wavelengths, so UVA is the longest and UVC is the shortest. You may have even seen UVA and UVB on sunscreen labels. They're what causes sunburn and can cause skin cancer. UVB and UVC are not only incredibly damaging to us, but they mess with all sorts of stuff, including photosynthesis and the productivity in plants and crops. They damage DNA, suppress immune systems, and can even reduce survival rates. In fact, UVC radiation is used to disinfect hospitals. The reason being is because it can quite literally kill nearly everything. And here's where the ozone layer comes in, because it screens all of the most harmful UVC radiation and the vast majority of UVB. Quite simply, without it, the radiation would literally sterilize the Earth's surface. But here's the thing, ozone is what's known as a trace gas. That means there's not a lot of it, basically. In fact, even in the stratosphere, ozone concentration is only about 15 parts per million. If you took all the ozone in the world and spread it across the Earth's surface like a kind of ozony jam, it would form a layer only 3 millimeters thick. That's the same as 2 tiny pennies. And if you did that same thing with the rest of the atmosphere, that atmospheric jam would be 8 kilometers high and very sticky. So what happens when you discover some of that precious ozone is missing? This animation on your screen shows the actual hole in our ozone layer, tracked over 2 decades. The blue and purple mark the area with the least ozone. Now, technically this isn't a hole, I know, in shape. It's a region of exceptionally depleted ozone. But hole was snappier and, more importantly, more concerning to the general public. Now, in 1979, there was no significant hole at all, and then it just grew and grew and grew and grew, covering not just Antarctica, but occasionally stretching as far as South America or even New Zealand. By the year 2000, it measured 28.4 million square kilometers, almost 7 times the size of the EU or 3 times the size of the United States. Looking back with hindsight, it seems pretty obvious that this was a planetary scale emergency. But how did we even realise we had a problem in the first place? The answer, as with so many things, is science. We first started measuring ozone to try and understand more about how our atmosphere worked. By the late 19th and early 20th centuries, scientists had already established that stratospheric ozone acted as a vital shield against harmful radiation. In the mid-1920s, Gordon Dobson, a British scientist, invented a new type of spectrophotometer, an instrument that monitors UV levels from the ground to work out how much ozone there is in the stratosphere. More than a century later, and the Dobson spectrophotometer is still the foundation of the global network for monitoring atmospheric ozone even today. In fact, what are known as Dobson units are now the gold standard for monitoring the ozone hole. So 300 Dobson units is the ideal amount of ozone. It's what gives us that metaphorical 3 millimeter layer I mentioned before. Less than that, and you're in trouble. And we started spotting signs of exactly that kind of trouble in the 1970s and the 1980s. British Antarctic Survey scientists Joe Farman, Brian Gardiner and John Shanklin took the world by storm when their groundbreaking paper Large Losses of Total Ozone in Antarctica published in Nature in 1985. Working through a backlog of data from the Dobson spectrophotometer and the Haley base in Antarctica, Shanklin discovered a systematic and rapid decline in the amount of springtime ozone. In 1979 it was relatively fine, but by 1984 the stratospheric ozone layer over the Haley base was only around 2/3 as thick as in previous decades. Something was happening to our ozone, and it was happening fast. Between 1986 and 1987, the race was on to find out what exactly was causing the loss. Scientists were on the hunt for ozone depleting substances, or ODS. The BAS team had theorised that possible chemical causes must be considered, and they weren't the first. If you've heard of the ozone hole, then you'll already likely know that chlorofluorocarbons, or CFCs, were eventually found out to be the culprits, but they simply weren't in the public consciousness back then. They were an invisible part of our daily lives, used in aerosols and fridges, a sort of killer lying in darkness waiting. But way back in 1974, scientists Mario Molina and F. Sherry Rowland published a paper theorizing that chlorofluorocarbons could destroy ozone in the stratosphere, although their paper focused on chlorofluoromethanes only. Now, at the time, their theories were shot down by the industry, and they were denounced as scaremongers. Their work was literally called pure science fiction. As a side note, and I do quite enjoy this, Molina and Rowland were later awarded the Nobel Prize in 1995 for chemistry, so they did win in the end. Anyway, in 1986, Susan Solomon, a researcher at NOAA, led a team to McMurdo Base to find out exactly what was going on. See, Solomon had theorized that if CFCs were responsible for ozone depletion, then there would be high levels of chlorine oxide radicals in the stratosphere. And guess what? There were. Molina and Rowland had been right all along. So yes, there was a hole, and yes, it was caused by humans. Shock. But one question still remained: how exactly did CFCs do all of this? Before we get into the chemistry, if, like me, you're quite enjoying a rather more positive climate news story for once, and you fancy some more like this, well then, I've got more good news. I've been a member of Planet Wild now for quite some time. I think of them like crowdfunding but for nature. So every single month, their community of over 25,000 members, including me, fund a mission to restore nature around the world. They are making good news like this happen every single day. They also document their amazing work on YouTube so we can see the impact of our contributions in real time. In a world of bad news, it really does give me some hope because we can actually see the impact on the ground. Recently, they funded a breakthrough that could stop plastic before it ends up in our oceans. Just a great example of some of the work they do. It's incredible. And actually, I'm such a big fan of their work that I also kind of wanted to share it with you. So in this video, I've got a treat for you. The first 100 people to sign up using my code Astrum8 will get their first month paid for by me. Yeah, all you have to do is scan the QR code on screen right now or click the link in the video description. You'll get to see the result of your contribution in less than 30 days. And if you want to see them in action right now, check out that mission fighting ocean plastic with the link in the video description. So why don't we keep the good news going a little bit longer and head back to ozone. Let's do some chemistry, shall we? So ozone is produced when oxygen molecules absorb UV light from the sun and split into two single atoms. One then reacts with an oxygen molecule to become O3. Now, ozone is pretty unstable. If you add a bit more sunshine, it can split back into O2 with one lonely oxygen atom left sort of spare, allowing the cycle to begin all over again. It's like a self-replicating planetary sunscreen whenever you need it. Until you throw some chlorofluorocarbons into the mix, then things get messy. CFCs are one of those things us humans thought we were inventing to make life better, easier, and cheaper. They first popped up in the 1890s and came into widespread use in the 1930s, primarily used as coolants in refrigerators and air conditioners to replace toxic gases like ammonia and methyl chloride. They were also pretty effective in aerosols like deodorant and hairspray, making perfect propellants in the pressurized cans. It's important to remember when we look back at these things, and obviously hindsight's a beautiful thing, that at the time, CFCs were considered perfectly safe. They were wonder chemicals to some, non-toxic, non-flammable, and stable. CFCs are halogenoalkanes, which are molecules consisting of carbon, fluorine, and chlorine atoms. The carbon-chlorine bond is long and relatively weak. Now, these molecules can float up into the stratosphere, where the UV rays from the sun provide enough energy to break that carbon-chlorine bond. Bonds like the one between carbon and chlorine are called covalent bonds, and they consist of two electrons. When it breaks, one of those electrons goes to the carbon and one to the chlorine, giving them an unpaired electron each. Species like these are called free radicals, and they are very reactive. When one of these chlorine radicals collides with an ozone molecule, it breaks one of its oxygen-oxygen bonds, creating oxygen and a chlorine monoxide radical, ClO. This can react with another ozone molecule, producing oxygen and another chlorine radical, which goes on to react with more and more and more and more. In fact, just one chlorine radical can break down more than 100,000 ozone molecules into oxygen. Now, given it's necessary for life on our planet, you could be forgiven for thinking that more oxygen would be a good thing, right? Well, it's good if you're on Earth's surface and you need to breathe, but it's not so good in the stratosphere, where you'd rather have the ozone keeping those UV rays at bay. The ozone munching part of this story is one most people already know, but what most people don't realise is that while chlorine radicals do ultimately destroy ozone, they don't necessarily do it immediately. They require a very special set of conditions, and this is where Antarctica comes in. You may have noticed that the hole in all of these satellite images is always mostly over Antarctica, and there's a very good reason for that. Antarctica is the highest, driest, windiest, and coldest place on Earth. It's a continent with no countries and no permanent population to speak of, unless you count the penguins, which I do. So this can't be CFC ground zero. How many penguins using fridges and air conditioners and hairsprays? Well, here's what's happening. The Earth's atmosphere is continuously being stirred by winds, so ozone depleting gases could end up anywhere. 90% of CFCs and halons, their bromine equivalents, have been released in the Northern Hemisphere, Europe, Russia, Japan, and North America. They rise up to the stratosphere in the tropics, and they are then blown polewards. And as we mentioned, Antarctica is cold, very cold. In the long months of winter darkness, a whirlpool of winds called the polar vortex traps super cold air over this region, allowing the formation of polar stratospheric clouds. Now, these clouds are perfect for CFCs to start breaking down into those chlorine radicals. When the sunlight returns in the Antarctic spring, that chlorine that's been building up all winter starts to kick into gear, shredding through the ozone at an incredible rate. The hole just keeps growing bigger and bigger and bigger until it stabilizes with the weakening of the polar vortex as summer arrives, and then next year the cycle begins again. This is why the hole is seasonal, and that is why it's nearly always over Antarctica. But just because it's all the way over there in Antarctica on a largely uninhabited continent doesn't make the ozone hole any less dangerous, it just means it's further away. Plus, what are called finger extensions can shift and expand the hole over cities in New Zealand and South America. I mean, back in 2000, residents of Punta Arenas in Chile were warned to stay at home during one of the largest seasonal ozone holes on record. UV levels had skyrocketed into the danger zone. Quite simply, without action, this hole would have kept growing, not just over Antarctica, but everywhere. The warnings were stark. By 2040, the hole would have gone global. By 2065, the UV index in the US would be 30. Usually it's just 9. Strong enough to cause sunburn in cities like Washington, DC in just 5 minutes. DNA mutating UV radiation would be up 500%. There would be more cancers, more cataracts, more compromised immune systems. Plants, animals, and crops would struggle. Entire ecosystems would collapse. And it wasn't just harmful UV radiation that was the problem. By the late 1980s, scientists were already seeing wide-ranging climate impacts. Jet streams were changing. Australia got drier while parts of Uruguay, Brazil, Paraguay, and Argentina got more rain. The nature of the chain reactions meant that our atmosphere was already loaded with decades of CFCs yet to even make their impact. CFCs have a long atmospheric lifespan. They can hang around in the stratosphere causing trouble way after they were used down on the surface. CFC 11s can last 55 years and CFC 12s 140 years. Something needed to be done, and quickly. And surprisingly, well, it was. For once, the entire world quite literally came together to act. And it worked. In 1987, 197 UN member states adopted the Montreal Protocol, or, to give it its full title, the Montreal Protocol on Substances that Deplete the Ozone Layer. How grand. It was the only UN treaty ever to be ratified by every single country on the planet. This landmark global agreement introduced a plan for phasing out and eventually banning CFCs, with other ozone-depleting substances like HFCs or hydrofluorocarbons being added as they were discovered. Montreal was a real turning point, a plan to save the ozone layer. And guess what? All these decades later, it's still working. CFC emissions have fallen by an incredible 99% since the Montreal Protocol was implemented. And ozone-depleting substances in the stratosphere, well, they're falling too. Since peaking around the year 2000, levels have declined by about a third relative to pre-ozone hole levels. Yeah, as you probably already guessed by now, things had to get worse before they got better. All of those chemical reactions were baked into the system, but it could have been a whole lot worse. And this is where it becomes a proper good news story. Because the ozone layer hasn't just stopped growing, it's actually started healing. The Antarctic ozone hole has been slowly improving in area and depth, if you remember those Dobson units, since the turn of the millennium. Now, full recovery is still decades away, but it's tantalizingly within reach. It's predicted we'll see a return to 1980 values by 2040 for the global average. That stretches to 2045 for the Arctic and 2066 in the Antarctic, because yeah, those polar stratospheric clouds, well, they really make a difference. A recent MIT-led study published in the journal Nature added the cherry on top of the cake. Ozone layer recovery has been observed in the past, but this is the first study to confirm healing as a direct result of global actions rather than natural influences like weather. The team borrowed what are known as fingerprinting techniques from climate science, matching the specific pattern of ozone changes across different months and altitudes against what models predict. It helped researchers confirm and quantify the role of us fridge buying, hairspray using pesky humans. Basically, we broke it and then we fixed it. And this is all obviously great news, but what's more is fixing the hole in the ozone layer is even helping us with things like climate change. Another study published in Nature found that if CFCs hadn't been banned in the 1980s, they could have raised average global temperatures by another 2.5 degrees Celsius, which if you've seen this channel, you know we really can't be doing. We can't get complacent though. In 2025, the ozone hole was only the 5th smallest since 1992, and it was still on average 18.71 million square kilometres. That's still twice the size of the contiguous United States. In a cruel twist of irony, climate change isn't helping. Temperature, weather, shifts in the polar vortex, they can all cause ozone depletion. Extreme wildfires can be doubly devastating, producing pyrocumulonimbus clouds funneling a cocktail of chemical components into the upper atmosphere. Those compounds contain, yep, you've guessed it, chlorine, which reacts with the ozone to break it down again. It's also hard to account for rogue actors who might be ignoring the ban by still using CFCs illegally. In 2017, a crack squad of scientists at Bristol University noticed rising emissions of CFC-11, banned since 2010, and turned detective to trace it back to China. The factories were eventually shut down and emissions did drop, not just in China but globally. Someone else had been breaking the rules, but exactly who still remains a mystery. It's tricky because we all still want to have fridges and aerosols and foam insulation, but they all need some sort of chemical cocktail to make them work. Replacements for CFCs can have their own consequences. For a while, hydrochlorofluorocarbons or HCFCs looked like they might do the trick, but they were also found to destroy ozone, so they too had to be phased out. Then HFCs came along, but they were a potent greenhouse gas, so they're out too. Hydrofluoroolefins, aka HFOs, were mooted as an alternative, but they have another side effect in the formation of a forever chemical, trifluoroacetic acid. You might have heard of it as PFAS, a poly or perfluorinated substance that will never ever break down and is ringing alarm bells all around the world for human and environmental health, and quite rightly so. Now, looming over all of this is the meteoric rise of nitrous oxide, commonly known as laughing gas, but predominantly used in agriculture. In the last 4 decades, human-caused nitrous oxide emissions have soared by 40%. It's now the most significant ODS, or ozone-depleting substance, that we have, and it's not covered by the Montreal Protocol. In fact, the Montreal Assessment Panel says it's a serious threat for stratospheric ozone. Good, another one. But this alphabet soup of chemicals isn't the only potential ozone killer out there. To paraphrase Sir Isaac Newton, what goes up must come down. In 1985, the year the ozone hole was actually discovered, there were around 120 successful rocket launches. That's satellites, payloads, and a record 9 space shuttle missions. It was a busy old year for space. Now in 2025, an incredible 4,510 objects were also launched into space, overtaking the previous record in 2023 of 2,903. There's currently around 15,000 satellites orbiting the Earth, with another 50,000 set to join them by 2030. And once they're finished studying the planet or guiding your car GPS system, often satellites are allowed to fall into the atmosphere, and that's a problem. See, what happens when they do that is they burn up on re-entry, and as they do, they release teeny tiny particles of aluminium dioxide. And yep, you guessed it, what does aluminium dioxide do? Depletes the ozone layer. The problem is that the new generation of satellites are extremely short-lived, maybe 5 years, so dozens of satellites could be hurtling back to Earth quite literally every day, each one potentially destroying the ozone layer we've worked so hard to rebuild back up again. For now though, the ozone layer is still healing, and I think we have to take that as a win, while making sure that these new threats don't undo all of that hard work. The truth is, life is complicated, and us humans like to complicate it even further. The bottom line is that when you mess with nature, you're always going to pay the price. But on the whole, as climate change burns all around us, I'd like to think the healing of the ozone hole is still basically a good news story, and sometimes we just need a bit of good news, especially in climate science. So yes, we fixed the hole in the ozone. That's why we don't really hear about it anymore. But that doesn't mean we should just forget about it. This cautionary tale is a reminder that each one of our actions has an impact. I mean, who'd have thought a deodorant used in Detroit could end up destroying a vital part of Earth's life support system over Antarctica? We could have ignored the warnings, but we didn't. Collective action on a global scale turned the ozone hole into an environmental success story rather than a planetary emergency. This to me is unequivocal proof that science plus public awareness plus crucially political action can equal results. The only sobering thought is it happened once and it doesn't feel like it's going to happen again. If this same situation was happening now in 2026, would we all rally together in the same way? I'm not convinced. The success of the ozone hole shows what humanity is capable of doing when we all come together for one unified cause. My worry is that we don't do that enough. Let me know what you think in the comments about this ozone situation, and whether this is the only time that you can think of as well that humanity's come together for a wider, greater climate good, because I struggle to think of too many examples. Thanks for watching, and we'll see you in the next one. Don't forget, before you go, we have that great offer for you with Planet Wild. The first 100 people to sign up using my code get their first month paid for by me. So if this video inspired you, if you want to do something right now to help the planet, please do get involved.